My name is Tilman Milzo, or just Till. I want to present an open problem about guarantees for gradient descent in geometry. So let me start with what is gradient descent. So you have some function. We want to find, let's say, local minima, sometimes also local maxima, or let's say global maxima or global minima. So here would be the global minima of that function. And what we do is we start with some point, some feasible solution here, and we compute its gradient and then move in the direction of the gradient, hopefully go lower and lower and lower. And then if things work out, then we will end up in a local minima, or if we're lucky, in a global minima. This method is extremely fast in practice. Unfortunately, it may take infinite time in theory, and even if we get a solution, we do not know how far away are we from the potential optimal solution. We usually only know that we're locally optimal. There is a situation where maybe our function that we want to optimize is convex, and then gradient descent is fast both in practice and theory, and going to be reliable because there's the local minima is also global minima. So, but usually in practice this is wishful thinking, and we're not in that situation. So if we look at the research on neural networks, is usually the way that neural networks is trained is gradient descent, and what they showed essentially is if the layers and the weights are sufficient, then gradient descent works, and we are somehow in this nice situation, which is maybe a good motivation why, or a good theoretical explanation why gradient descent works so well in practice for neural networks. So now I want to apply this to geometry, specifically the art gallery problem. Here, let me repeat the definition of the art gallery problem. We've given a gallery that we want to protect. We protect it using guards. So guards we model by points, and points can see a different point, or a guard can see a different point if the line segment is contained inside the polygon. For instance, the green point can't see the black point there. And so the green guard sees this green region. All these four guards together, we say guard the entire gallery, or they see the entire gallery. And we want to find as few guards as possible in order to guard the entire gallery. Now, if we want to use gradient descent for this, we could start with one guard, we compute its area, and try to locally increase the area. There is a little bit of math involved, but if you move this now to a new position and you see more, then this should happen if you follow the gradient. You can also do with several guards. So here, in order to compute the gradient, you just have this orange guard, you move it to the right, then suddenly this purple region would be a new region that you see. So usually we would not expect that gradient descent gives us the optimal solution, but what we can hope for is that there's maybe this number c, let's say larger than 1, such that for any k-guardable polygon, if we use c times k guards, then the local optimum will be the global optimum, and then we would have found a c approximation. I don't know if that exists. If yes, then it would be an almost constant factor approximation. If not, it would be interesting to know how these polygons look like, where we cannot, where these c could be arbitrarily large. Maybe what's the smallest k where this can happen, or is there maybe a function of k such that if we have f of k guards, the local optimal will be the global one. Either way, I'm very curious about whether local and global optima are the same here. I think it's a nice combinatorial question, and I would have some nice or interesting algorithmic consequences. And thank you for your attention.